Okay, in today's video, I'm going to go over a brief explanation and introduction to linear momentum, and we'll also do a short example problem at the end of this video. The first thing I'd like to start with is just a couple simple definitions of momentum. Momentum is a quantity of motion arising from its mass and its velocity. That means basically for an object to have momentum, it has to have mass, which all objects have mass, and then it needs to have some velocity or it needs to be moving. Okay, so it's just mass and velocity. It's pretty, maybe the word momentum sounds a little complicated, but it's pretty simple in its sense about how we calculate momentum. And momentum is directly proportional to the object's mass and its velocity. So the equation we use is just P. P is a symbol for momentum, is equal to m times v, which is the mass times the velocity. You can see we said it's quantity directly related to its mass and its velocity. Okay, so let's just go over a little more specific information about the details of momentum. Again, here's the equation. P is equal to m times v. Now, I don't know why they use P for momentum, but they just do. So that means the symbol for momentum is P. And the metric unit for momentum, because it's mass in velocity or mass times velocity, is just the kilogram, because that's the base unit in the metric system for mass, times meter over seconds, or meters per second, because that's the units for velocity. So it's just kilogram meter per second. There's no like joule or other kind of Newton watt kind of name for it, just kilogram meters per second. All right? There's no abbreviation. It's a vector quantity. Momentum is a vector, so it has to be defined by its magnitude and its direction. And there is also something called conservation of momentum. So we have a system and things interact. This kind of comes into play when we talk about interaction of objects, which we'll do in future videos. There is conservation of momentum. Momentum is conserved just like charge, mass, and energy are conserved. All right, and let's say just quick little calculation here how this kind of works out. The momentum, which is the mass times the velocity, I think I imagined this was a bowling ball which had a mass of 6 kilograms. It's moving at 2.5 meters per second, then simply its momentum would just be 15 kilogram meters per second. And I said it was a bowling ball, and it has to have direction. I didn't say it was moving to the east or the west, the positive negative, we'll just say down the bowling lane, like that. So that's really simply how we just calculate momentum, and that's the introduction and the specifics for momentum. Now let's just do another kind of interesting example here. For momentum, here's our equation, P equals m times v. This is a cannon, which is going to shoot a cannonball, obviously, and this is Usain Bolt, and Usain Bolt runs the 100-meter dash. And we're going to compare the momentum of these two objects, one being the cannonball, which has a mass of 5.5 kilograms, and there's a muzzle velocity, or velocity of the cannonball is 250 meters per second. Now, Usain Bolt, I looked online, he has a mass of approximately 94 kilograms, and he runs the 100-meter dash, and he does that in about, or I guess that's his world record, is 9.58 seconds. So now we can calculate the momentum of each of those objects. The cannonball is 5.5 times 250, and that gives us a momentum of 1375 kilogram meters per second for the cannonball. And Usain, his mass is 94 kilograms. This would be his average speed if he does the 100 in 9.58 seconds. Multiply those two, and you get that he has a momentum with his mass moving at that velocity of 981 kilogram meters per second. So you see we have two different objects, one being much bigger than the other, but the other one, the smaller one, having a much higher velocity. So it has more mass, more momentum than the more massive object. So it kind of tries to show you that it depends on its mass and its velocity, its mass and its velocity. And we can figure out how much more mass, relatively speaking, the ratio of those two for the cannonball to Usain Bolt. The cannonball has a momentum about 40% more, 1.4, factor 1.4 more than Usain Bolt. So I thought it would be interesting to see like how fast would Usain have to run, or at what time would he need to complete the 100-meter dash to have the same momentum as the cannonball. So we're going to try and change this time, which will of course change his velocity, but we'll go based on the time as kind of the end thing. What time would he need to complete the 100-meter dash to the same momentum as the cannonball? So it's 40% more. So just going to take his mass, multiply it by this factor, and that means he would have to run not 10.44 meters per second, but actually 14.62. So 14.62 times 9.4 will give us 1375. That's how fast he would have to run, and that would have to be his velocity. But what would his time actually have to be to achieve that velocity? We can use our equation for the velocity as the distance divided by the time, or the change in position over the time. We want to know the time, so we rearrange to the time. We get the distance divided by the velocity. The distance in 100 meters, and his velocity, which we calculated up here, is 14.62 meters per second. That means that he would have to complete the 100-meter dash in a time of 6.84 seconds in order to have a velocity of 14.62, which when multiplied times his mass of 94 would give it the same momentum as the cannonball. Okay, he couldn't, of course he could change his mass, but we really don't think of things changing their mass so much. We want to change the velocity for this time. Okay, so there you go. That's a brief introduction into momentum, kind of the definition, the symbols, the units, and then a quick calculation. And the coming videos we'll do some more complicated calculations with momentum, forces, impulse, and collision of objects. All right, so thank you very much for watching. I hope you found that video helpful. If you did, please do all the following 4 things. Subscribe to my channel, get all my excellent chemistry, physics, and math videos. Give me a thumbs up for this video. Leave me a positive comment in the comment section below, a nice positive comment. And then don't forget that sharing is caring. Share this video with all of your friends. Show them how much you care. Thanks for watching. We'll see you in the next video.